All right, so we want to make you aware that we have a wealth of expertise in our area. In particular, our field engineers are a community of global specialists in Swagelok products and applications that complete extensive training and collaborate with each other and Swagelok to help our customers create reliable systems and solve tough challenges related to fluid systems. In Southern California, we have two local field engineers. Mark Barron is our presenter this morning. He has over 18 years experience with Swagelok. He's held technical responsibilities in assembly and fabrication, quality, project management, and account support. Also on the line with us this morning is Jonathan Burris, who's our Director of Engineering. He holds over 20 years engineering experience with the Master's in Mechanical Engineering from UCLA and an MBA from UCSD. And John's going to join in at the end to help us answer questions as they come in. These field engineers cover the counties of Orange, San Diego, Riverside, most of San Bernardino, Imperial, and Baja, Mexico, with San Diego Fluid System Technologies. And now I'm going to pass it on to Mark to take you through our presentation.
Good morning, everybody, and thank you, Jen, for the warm introduction, and thanks again to everybody for getting signed up to join us to discuss some interesting topics related to regulators. I do want to point out this is intended to be a basics class, which is why it's pretty abbreviated. But this will actually be the first in a series of installments because each topic that we'll discuss could easily be the star of their own on their own webinar because we could really take a deep dive on any one of the topics. So why even have a webinar specific to regulators? I think of a comment our product manager once made at Swagelok stating that 95% of the regulators that get sent back to Swagelok for evaluation are either one, at the very beginning of their life, or two, at the far end of their life. What I actually hope to teach everyone today will impact the segment of regulators in the beginning of their lives. Basically, making sure that we're picking the right regulator for the application and ensuring that it performs as we expect. So just a quick overview on the agenda of what we hope to accomplish in today's session. We're going to talk about what needs to be known about your fluid system, which will then become inputs when you need to properly specify your regulator. Of course, we'll touch on regulator theory, introduce you to main categories of regulators. Then we'll talk about performance criteria in the form of lockup and choked flow. We'll talk about droop, and we'll talk about supply pressure effect. We will address how this criteria can also be managed, and then we'll have time for questions at the very end. So moving on to what's needed to select your regulator. And I kind of think about how I used to pick regulators, and granted, this was before I learned the intricacies of the regulators and really more importantly understood them. I'd often go to my box of regulators and search for one thing: outlet pressure of what I was trying to accomplish. And this approach just simply isn't good enough. I may have gotten an okay result, but really it could have been much better. When investigating a regulator for your application, be sure to understand the flow that you need. This could be a single value, but depending on the process, you may want to consider flow as a range. Inlet pressure, of course, is an important piece from the perspective of safety. Of course, you never want to select a regulator rated less than your inlet pressure, but picking something close to your system pressure will actually provide better results. Outlet pressure, in general, you want to be as close to your desired pressure as possible. Speaking of media, most manufacturers usually create gas flow curves using air or nitrogen and hydraulic curves using water. If the system media is a different fluid, it may be necessary to adjust the flow scale to account for the differences between the specific gravity of the actual system fluid. Like media, temperature may also require some sort of a correction factor outside the range of lab conditions. Accessories is a big important thing that you want to always consider as well. How are you going to relieve downstream pressure? Relief valves are a good method of doing that. What are you going to do as far as managing and monitoring your gauges or your inlet and outlet pressures. Do that with pressure gauges, block valves, and of course hoses for making connections. Before we move on to the next slide, I want to introduce you to a typical regulator flow curve shown on the right-hand side of the slide. It's plotted with outlet pressure in my y-axis and flow in my x-axis. This actual application shows a regulator set at 75 psi. You can see that over on the far left of my graph, and it's set under static conditions. Now, as I introduce flow and slowly, gradually increase flow, I get a curve, and this curve represents the drop of outlet pressure that I set at the beginning as my flow increases. This term is known as droop. We're going to learn a lot more about it in some coming slides. At the far right side of my flow curve is another term we're going to talk about, is choked flow. And then that first area that I talked about on the far left is known as my lockup zone. These are basically the areas on the flow curve that we don't want to be operating. Again, we'll talk more about these on the upcoming slides. So moving on to regulator theory, regulator is just a purely mechanical device whose main purpose is to maintain a constant pressure on one side of the regulator, even if there's different pressure or fluctuating pressure on the other side. In the case of a pressure reducing regulator, pressure is controlled downstream of the regulator. The schematic on the right shows higher pressure source of gas coming from your bottles and then going through a pressure reducing regulator to control my process. A back pressure regulator, on the other hand, uses the process pressure as its inlet and senses and adjusts when the upstream pressure increases. It's important to note that this presentation applies specifically to pressure reducing regulators, with the exception of this introduction to back pressure regulators. And the reason I note this is because the flow curves that we're looking at are going to be for pressure reducing, and they would look different if they were for back pressure regulators. More on basic theory. If we take a look at a section view of a typical regulator, there's four main components that I want to focus on in our pursuit to understand how a regulator works. I'd like to break this down into two main categories. One is my control element, and it's made up of a seat and a poppet. Next is a load and sensing element. That's made up of a range spring and a diaphragm. The range spring could be gas in the case of a dome-loaded regulator, which we'll learn about shortly and how it helps us to minimize droop. Also, the diaphragm in this case could also be a piston if we get into higher outlet pressures. Moving on to my operating principle, the balance of forces. When learning regulator performance, I found this equation to be extremely helpful. And I'm going to go through it real quick. It's my range spring force, which is noted in red, is F1. This is equal to the poppet spring force, F2, noted in green, plus my outlet pressure force, F3, noted in blue, and F4, inlet pressure force, F4, also noted in purple. And it's important to note, as I mentioned, this is a balance of equations, or a balance of forces rather. So when one changes on one side, it's going to change something on the other side. And that'll be important to note when we work through some examples. So it's one thing to learn the definition of droop that we'll talk about shortly. That's your increase in flow caused by a decrease in outlet pressure. Or actually, when you increase flow, you get a decrease in outlet pressure. And it's fine to understand a definition, but to really understand this formula and note that F1 will increase when downstream flow increases, which is required for the poppet to open and allow flow. Now, because you have a balance of forces, F1 drops and then F3 will drop too. I've got a neat animation coming up here in a few slides that'll help understand this better, and we'll also see this formula again throughout the presentation. So if it's a little confusing right now, hang in there. As a result of going through this, it's going to be useful for, one, troubleshooting your system, and also considering how a regulator will perform if your system variables were to change. So let's get into our first term. I like talking about lockup and choked flow together because of their relative position to one another on my flow curve, the far left and the far right, basically where we don't want to be with our regulator. On the right, we see a typical flow curve, two to be specific, and it's important to note that these are independent of one another. They're there to fit two or more scenarios onto one graph. This graph is outlet pressure in the x-axis and flow in my, outlet pressure in my y-axis and flow in my x, just like we saw earlier. So regulators always perform best at the flattest part of their curves. That's the least amount of impact that they'll see from changing variables. On the far left is our lockup zone, which sees a steep drop of pressure immediately after flow starts. Remember when we set that pressure in a dynamic or a static application? Now as we apply flow, we get this steep drop. You never want to have your regulator working in this area. In fact, a regulator operating in this steep drop may emit chattering or pulsating sounds as it fluctuates between flow and no flow conditions. So lockup, by definition, is your difference in pressure between a flowing and a non-flowing condition. So when flow is stopped and your outlet pressure begins to build, the balance of forces that we talked about favor the control element, which allows the poppet to seat itself and close off inlet pressure. Simply stating, if I shut off my V2 valve, my P2 is going to increase. Choked flow occurs on the far right of the curve. At this point, the flow demand has exceeded the pressure control capabilities of the regulator. Here the regulator is wide open and it's no longer even regulating pressure. Essentially, it's changed from a pressure control device to an open orifice. Increasing downstream flow to this point or beyond renders the regulator ineffective. It's not advisable to operate a regulator in the choked flow area due to the sharp pressure drop. Note that flow coefficient is measured at a regulator's fully open position, and that's why it cannot describe the overall performance of regulators. In fact, selecting a regulator based solely on its flow coefficient can result in unsatisfactory performance. If a system flows within the range of the regulator's C sub V, the flow coefficient, one may believe that the regulator is right size, but that is not necessarily true. The CV represents the regulator's maximum flow capacity, and remember, at maximum flow, a regulator can no longer control pressure. So now that we've learned about lockup and choked flow, let's discuss dealing with each one. The first rule of dealing with any regulator criteria is understanding the impact. And today's webinar is actually a pretty good first step in achieving expertise in the area. For both lockup and choked flow, always try to operate in the optimal part of the flow curve. Remember, this is the flattest part and it's ideal. Lockup can come quicker with a soft seat material like an O-ring versus PTFE, but as with any material selection, there's going to be pros and cons on any material. Also, make sure your regulator is right sized and you're not basing adequate flow on the published CV. Okay, so we've talked about that sweet spot on the flow curve, right? That's the flat spot of the curve, but it's still a slope. This downward slope is known as droop. As your flow increases, your outlet pressure will drop, some or even a lot, depending on the regulator design. While droop is relatively modest along the flat part of the curve, it is quite steep at the far ends of the curve. Supplying a regulator with pressures substantially lower than the inlet pressure rating result in a flow curve with more droop than flow curves for regulators whose inlet pressure ratings closely match the actual system pressure. In addition, selecting a regulator that closely matches the inlet pressure requirement provides the best handle resolution, smaller amounts of pressure change per turn of the handle, giving you better control and enabling a broader ideal operating range. So this droop is primarily caused by a set spring, and it's due to the stretching of the set spring, which equals lower force and a reduced outlet pressure. We'll talk about mitigating droop on an upcoming slide. Good. We have our balance of forces equation again. So I'm going to talk through this, and then on the next slide, we've got an animation to explain it as well. So let's see what happens when we increase our flow. The first thing that's going to happen is my poppet is going to open. As a result, my range spring stretches to account for this downward movement of the poppet. So what happens is the range spring stretches. It's going to loosen its load force, and because of my balanced equation, if F1 goes down, so must my outlet pressure, F3. So summing up, droop back to its definition, it's the drop in outlet pressure due to my increase of flow. Hopefully this equation is starting to make more sense, and I'll share with you a neat animation here on the next slide. So as you open your regulator, you get a flow through it, and you see the change in pressure on the downstream side. A close-up view, you could see the poppet moving up and down to allow flow through the regulator. That was the motion that I was speaking about that transfers to the spring force extending and therefore loosening and therefore affecting the balance of forces. So what have we learned that we could apply or to address droop? Well, you can adjust the regulator with your process flowing. This might be an okay solution, but it could be completely impractical based on the location of your regulator in your system to adjust it every time your flow changes. 2, you can always shoot when picking your regulator to stay in the sweet spot of the flow curve. Again, this is the flattest portion. 3, you could pick a regulator whose inlet pressure rating closely matches the actual system pressure. The idea of picking a 3600 psi inlet seems great to accommodate more conditions, but in reality, you may have to take a performance hit. I used to pick regulators based on this criteria myself, and now that I've learned that it's not ideal and it impacts negatively droop, I know better to pick my inlet pressures closest to my system. We could use a dome-loaded regulator. As we noted, the change in spring force impacts the droop the most. Therefore, using a dome load is a gas-sealed dome that applies your force and eliminates the need for a spring. We actually have an example of a dome-loaded regulator on the right, where we've got a red regulator that's providing force up above the diaphragm instead of having a range spring up there. External feedback is an addition to the dome load that actually then ties dome pressure to your downstream pressure. So as your downstream pressure changes, it's constantly monitoring and adjusting. Again, it's all about what your process can tolerate. Supply pressure effect, which is also sometimes called dependency, is a ratio describing the change in your outlet pressure per 100 psi change in your inlet pressure. In other words, for every 100 psi drop in inlet pressure, the outlet pressure will increase by X psi. X is the supply pressure effect. For standard pressure reducing regulators, the outlet pressure increases as your supply pressure decreases. The opposite is true as the supply pressure increases. This effect can also be realized on system startup or shutdown. The regulator should be set to the off position before turning the supply pressure on or off to prevent overpressurization of your regulator diaphragms, outlet pressure gauges, or any other sensitive equipment downstream. I talked to a salesman the other day, and he mentioned that his customer sets his regulator throughout the course of the day, and at the end of the day, he simply shuts off his block valve on his cylinder without turning the regulator off, because in the morning when he comes on, it's one less thing to adjust on getting the process going. This is a risk. If you open that valve, there's a brief moment before the regulator starts performing its functions where the system is going to see high pressure spike. So that could damage the diaphragms, or it could damage your gauges, or again, if there's sensitive equipment downstream like analyzers or other electronics. Also, when selecting an anti-tamper model, it's important to make sure that the supply pressure effect will not cause excessive overpressurization on opening and closing of the supply pressure. So let's see how this calculation applies to the following scenario with a single stage regulator. Let's say I have a supply gas coming from a cylinder, and that cylinder has 3,600 psi. Next, we adjust our outlet pressure to our process of 50 psi. Now, as we run our process for a period of time, my cylinder pressure is depleted to 2,600 psi. So let's apply the formula to see what impact is in our 50 psi outlet that we had. The inlet was 36, now it's 26, so the delta P is 1,000 psi. You apply the supply pressure effect percentage to this number. So in this case, we've got 1% supply pressure effect, we get a 10% change. So now my outlet pressure, which was 50, is 60. And the question is this safe or not? And it really depends, again, on what's downstream. So what can we do to address supply pressure effect? A few things. Again, one, you could stand there and adjust the regulator. Again, we noted that's not always practical. Two, we can move to a two-stage solution, which we'll demonstrate on the next couple slides. Or three, you can move to a balanced poppet design, which changes the surface area in which the pressure can be applied to the poppet, and therefore you could actually decrease your supply pressure effect. That last one, however, is a design feature of the regulator. So let's see what we can do to apply a two-stage solution. So let's see how this applies to the following scenario. Now we've got supply gas coming from a cylinder, and that cylinder has 3,600 psi. So we set our middle stage to 500 psi, and we set our second stage to 50 psi. It's two regulators in series. Now let's see how the inverse of the supply pressure effect will actually work in our favor on the next slide. So now that we've depleted our source from 3,600 to 1,600, so our delta P is 2,000. And again, 1% of 2,000 is 20 psi. So my middle stage has gone from 500 to 520, completely predictable based on what we've learned on the last few slides. But now let's look at our second stage regulator. The inlet is now 520, but instead of going down like the cylinder did, our pressure is rising. Because of the inverse relation, we still see a decrease in pressure on the outlet, but it's 1% of the 20 psi, which is only 0.2 psi. So in the end, our outlet pressure only dropped 0.2% while handling a 2,000 psi change on the inlet. This is the last topic that we're going to talk about before we get into some of our questions. Keep in mind as you do make notes, if you have a specific area that you'd like us to cover in our next series, please provide that feedback either in the Q&A or separately by way of email. We'll share our email addresses with you on an upcoming slide as well.
All right, thank you for reviewing those concepts in such great detail, Mark. While you take a look at any questions that have come in, I wanted to make sure everyone in attendance has our contact information. So feel free to note those email addresses, and you can reach out to Mark or John directly if you have further questions for them. On the right-hand side, I have noted a few resources that are available for our customers. On swagelock.com, the direct Swagelock website, in the toolbox area, there is a flow curve generator tool that you can use to help create your flow curves as needed for your organization. We encourage you to check that out. There's also a good technical bulletin available on regulator flow curves. If you go to swagelock.com and just type in MS-06-114, that's the most direct way to get access to that bulletin. Likewise, the catalogs for several of the common series of regulators are noted below, and you can find those easily by typing in the catalog numbers if you want to note those. We'll also follow up with an email for you with the recording of this webinar, as well as direct links to these resources. And there's also a good video, which you saw a snippet of halfway through the presentation, on flattening regulator flow curves to minimize droop on SwageLock's YouTube channel.
All right, thanks a lot, Jen. I've got some good questions. A lot of people are very interested in the swag, so I think what we're going to give up is are some cool SwageLock hats. John Burris is going to join us here in just a second to help answer some of the questions. There's only 3 so far, and 2 are coming from Pradeep. So Pradeep, thanks for these questions. John, I think you're still muted, but be prepped for this. So Pradeep is asking, what if I have a mass flow controller connected to my gas line? Will this change the outlet pressure? So a mass flow controller connected to my gas line, what will be the impact on my outlet pressure? I guess I'm thinking through this. You have mass flow controller, so that's controlling your flow. We know a regulator's main purpose in life is to adjust pressure and not flow. So downstream, I have my mass flow controller controlling my flow. I would suspect that depending on the flow change, you're going to see the outlet react, or the pressure react properly. It's just going to be operating along a different range. So that flow curve that we looked at earlier will be working along, we'll be working on it from left to right. So hopefully that answered your question. I may have butchered it. I'm happy to come back and address it here for you offline too. We'll follow back up with you. Pradeep also said, I rarely see a double regulator setup. How common is that? And we were running the example of the 2 in line because the schematics or the animations we show of the increases and the decreases through the various stages is easier to understand when you've got 2 regulators side by side. It's pretty uncommon as well, at least from my perspective. A lot of times you'll see a dual stage regulator, which has those 2 same regulators just at opposing ends. So one's a line regulator and then one's the first stage regulator. So good question. The last question we see here is, what should be done with the regulator on startup? You mentioned the regulator could be damaged when opening the valve at startup. Yes, thanks. Good question. So if in the instance that we talked about earlier, if I don't shut off my regulator, so my regulator has a set pressure and I'm happy with it, if I just shut off my cylinder and leave my regulator in an open state, when I come back tomorrow and I open up my bottle pressure, there's going to be that first big spike of pressure that comes to the regulator. And depending on the sensitivity of the diaphragms or the gauges or your downstream equipment, you could actually damage those. Let's see, a few more questions have come in. What are the advantages of using a pressure reducing regulator over an expander? That is a good question, and I don't know the answer to that. Let's see, over an expander. That is Sergio. Sergio, can you clarify what an expander is? I'm not quite sure I understand. And we'll come back to that question too. Dan Bannon, it appears that we didn't address a venting option. That's a good point. So of the regulator, when the spring pressure is lowered to the point of venting in a standard range. Dan, we're thinking about doing a separate topic of how to select or how to choose when you want to vent your regulator. I know in most cases, I always prefer to have it vented. So what that means is, remember my slide earlier where I had downstream V2, that was my flow control. And when I shut that flow off, my outlet pressure begins to increase. What's nice is to have some sort of a venting feature to relieve that pressure, and that could come in a couple different forms. One, it could be a vented option if you're dealing with a media that's safe to vent to your atmosphere. That's not always the case. So other times you might have a built-in relief valve that captures the release of the media and then routes it to a common vent area. You also have an option for captured vent in most regulators, which kind of performs the same function of what I explained there with a relief valve. Good question. I like that one. And let's see, Alexander, when choosing a regulator, what is a good rule of thumb for picking the outlet pressure specification? You know, it's always good with any of the criteria to pick anything that's as close to your desired pressure as possible. So if I'm trying to run a 10 PSI outlet and I've got an option for a, say, 0 to 25 outlet or a 0 to 50 outlet, I'm going to want to pick the 0 to 25. I know it could be desirable. You think, well, if I get the 0 to 50, it gives me options in the future. But as I mentioned, you could have a negative impact, like we talked about with droop, and picking an inlet pressure that's different, far different than your system pressure. Let's see, for a block valve, you are recommending using a needle valve to slowly increase the flow of the regulator. You could, that's ideal, something slower moving. This is the question that came up with regards to the block valve. You don't want something quarter turn fast acting for the same reason that we don't want to introduce the system to a quick and abrupt spike. So having a multiple churn control valve, oftentimes on your cylinders, you have a rotating handle that's multiple churns versus a quick acting quarter churn. Hope that answered that question. And let's see, we've got one additional. I've used the 2 regulator setup when the pressure differential is high, allowing the higher pressure regulator to take the abuse and the second regulator being able to control more accurately. That's cool. That's a good example that one of our attendees noted here, Pradeep, that might be an instance where you would run 2 regulators in series, let one take the brunt and then have the second one controlling more accurately. That came from Dan Bannon. Thanks, Dan. That was a good one. And coming back to the expander versus the regulator, so I didn't see anything coming back on that, clarifying what the expander is. So what we'll do is we'll circle back with you and get in touch. If we don't have your contact information, definitely use the email that Jen has provided for both myself or John or even Jen herself. And we'll gladly circle back to you and answer all your questions. Sorry, I didn't understand the expander question there, but hopefully we'll get you answered up here offline. So thanks again for everybody who's joining. Again, please do submit feedback on what you would like to hear as the future webinars for further deep dives on the pressure regulators.
Thank you, everyone. Have a wonderful day.